couple of things here. I think we talked a little bit about enthalpy. This is back from, I think it's your chapter 5, if I remember correctly. So when we break apart the intermolecular forces in our liquid solvent and in our solute, both of these are positive delta H's. Whoa. So that means that energy is required to do that. Oh, what did I do? Okay. I swear, something's new every time on this thing. Then when we allow the solution to form and we allow our solute and our solvent to interact, we're going to release energy. So this is going to be a negative delta H. So these are positive and then negative. But that still doesn't necessarily tell us if a solution is going to form. You're right, I totally see. Good job, guys. Okay. So this is basically the energy diagram for this slide. So we have to consider a few things here. So I mentioned that this solution feels hot. It's not exactly the same thing as what we're going to be talking about here in terms of mixing, because that's essentially the opposite of that. But when we talk about our positive enthalpy of solution, that is when we consider, oh my goodness, this is totally throwing me off. So delta H of solution is going to be a combination of the delta H of the solvent, so again, that's negative. Delta H of the solute, that's also negative. And delta H of mixing, so that's positive. Okay, so minus VE negative plus VE positive. Sort of a shorthand I learned when I was in college, and I can't break myself of it. Okay, and so we can have energy absorbed. Our solution will feel cold, and we can have energy released when we form a solution, and the solution will feel hot. Yes?
You said in the previous slide that the solvent is soluble in oxygen.
What is different today? Yep, these are totally backwards. Okay, now why doesn't it erase? There, okay. Oh my God, showing my old. Okay. Sorry about that. And this slide. All right, so when we're forming solutions, especially when we are talking about salt solutions, these ion dipole interactions are going to come into effect. So that was one of the main reasons why we brought that up from chapter 11 with our intermolecular forces. You've seen figures, if not this figure, something very similar to this, where we have our cation in a solvent cage where the oxygen with a negative dipole in water is directed towards that positive cation, and then vice versa for the anion, where the partial positive of the hydrogens in water is directed towards the anion. And that's important because this type of interaction is what actually allows the solvation to occur for an ionic substance. So what I'm showing here in this figure is a crystal of lithium fluoride. Okay, and what we're going to see is water molecules interacting along the edges of that crystal. And you'll see the proper orientation of those water molecules around each type of anion or cation. And eventually, as it's sort of showing down here in bottom right, enough water molecules will surround an anion or cation in a proper orientation so that it will actually be drawn more towards the water, and that solute-solvent interaction will be greater than the interaction of the solute by itself or the solvent by itself. Okay. So let's take a look at what's actually happening at the particulate level in terms of forming solutions. So we're going to have two different substances. We're going to have a salt, sodium chloride in this case, and sugar, C12H22O11. Both solids, we're going to dissolve these in water, and we're going to compare the differences. One thing I want to point out, this structure of sugar, what in the world? Okay, why is it gray? It's black. Okay, oh God, I'm losing it. Anyway, look at the structure, okay? So what kind of bonds do you see? In terms of intermolecular forces, what should we be seeing? We've got an oxygen-hydrogen bond, so we're going to have the possibility of hydrogen bonding. And that bond is also polar, so we can have dipole-dipole interactions. And, of course, everything has London dispersion forces. All right. So I don't have the structure show up again, so I kind of wanted to put that out. So let's take our sodium chloride and let's put it in water. Let's allow the water molecules to surround the solid, start drawing those ions off like in a couple slides previous. And we're going to put our sugar in solution as well and see what happens. What's the main difference? Still gray. Yes?
With the sodium chloride, the atoms split apart, so it dissolved.
Mm-hmm.
But the sugar didn't change at all.
Sugar didn't change at all. So when we have our sodium chloride, we formed ions. Our sugar is a covalently bound molecule. When we dissolve that type of molecule with covalent bonds in it, we don't see any ions formed in many cases. Okay? That's not always going to be the case. But in the case of sugar here, no ions are formed. This is going to be important when we talk about colligative properties, which is going to be section 5, I believe. It's going to be important to recognize how many ions, or not, are formed when you dissolve a substance. When we dissolve sodium chloride, we get 2 ions for every 1 unit of sodium chloride. So we get a positive sodium ion and the negative chloride ion. Okay? And like I said, that's going to come back in section 5. Okay, so we've been talking about our intermolecular forces. They're huge. They're really important when we're thinking about solution formation. So in your notes, take the time here to write out what type of intermolecular forces are present between solute-solute, between solvent-solvent, and then finally what's formed between the solute and the solvent. And it's going to be different for the salt versus the sugar. Let's take a few minutes and do that. And I'm going to play with this thing and figure out what I'm doing. Oh, I got it. There we go. Talk with your neighbor here. Make sure you're coming up with the same things. Okay, what type of intermolecular forces are present in the solute in the salt, in sodium chloride? Solute. What kind of attractions? Oh yeah, there we go.
There would be dispersion forces.
Yep.
Dipole.
I'm going to go with you on dispersion. It's not quite dipole-dipole. We do have an ionic bond present. So we've categorized that previously as an intramolecular interaction, but that is important. Yes. It's not. There actually isn't a dipole here. Those are only going to show up in our covalent bonds. Okay. What about in the sugar? Now you're all afraid. Sorry. Yes. Dispersion. Got dispersion. Hey, right. What else? Yes. Hydrogen bonding. Yep. And dipole-dipole. I'm just going to write D-D. Yes.
Does NaCl in a solid form exist in a lattice?
Yeah, so in the solid forms, sodium chloride is in the crystal lattice, yes. Say that again?
But we wouldn't count ionic as solute-solute interaction.
Right. We wouldn't count the ionic bonds as intermolecular interactions. That's going to be intramolecular, so yeah. Yep. Solvent. They're the solvent's the same in both of these figures, examples, so what do we have? Our solvent's water. I'll write it down before you say it. Dispersion. We've got dipole-dipole, and we've got hydrogen bonding. And that's the same on both. All right. Solute, solvent. What's the interaction here for our salt water, salt plus water? Ion dipole. Anything else? There are dispersion forces, but we don't necessarily call those out when we're talking about a mixture. Okay. So this is, what's that? You do not have hydrogen bonding with the solute and the solvent. So there's no hydrogen bonding between ion and dipole. So really, ion dipole is the only intermolecular attraction that we're going to concern ourselves with here. And then in the sugar, what do we have? Dispersion. We're still going to have dipole-dipole. Actually, I take that back. I think I've got a mistake in the next slide as well. But we will have hydrogen. We have the possibility of having hydrogen bonding. So again, dispersion is not occurring between solute and solvent necessarily, so we can ignore that one. Okay. I took it back.
Oh, okay.
Sorry.
So it's just hydrogen bonding.
Hydrogen bonding. Oh, Yeah, no, I took back the wrong one. Hydrogen bonding and dipole-dipole are present. Yep. Okay. On any of that? Yes. All right. So the next couple of slides here are going to look at some energy diagrams for some general examples. Okay. In our plots, we have enthalpy, enthalpy on our y-axis. Our x-axis is not really a thing. It's just showing the differences here. The first example we're looking at is for an exothermic process. So will an exothermic feel hot or cold? Hot. Okay. All right. So again, this is breaking up our solute, our solvent, and our mixing. So we're going to look at the effects of each of these things. When we separate our solvent, okay, we have some amount of energy that needs to be applied, and that's given by this blue arrow. Okay. Same with our solute. We've got a green arrow representing the amount of energy that we need to use to break up that solute. And then this sort of light blue arrow is just the sum of those two delta H's. Okay. And then the orange is giving our enthalpy of mixing. Okay. And in this case, and this is something you have to determine experimentally, in this case the delta H of mixing is large. And so we end up with delta H of solution that is negative. Okay. Let's see. Quick, guys. All right. So we've got our positive delta H for our solvent, positive delta H for your solute, and a negative delta H for mixing. And that negative delta H for mixing is quite large, and it allows for the exothermic process. But that's not always the case. We don't always have exothermic when it comes overall energy of solution when we form a solution. So in the case where we have an endothermic process, okay, in this figure, essentially delta H for the solvent and for the solute are the same, but our delta H of mixing, okay, is going to be smaller and doesn't result in a negative delta H of solution. We end up with a positive delta H of solution. But if we look at a specific example, ammonium nitrate, okay, if it's endothermic, does it feel hot or cold? Cold? This solution does form, okay, but in terms of enthalpy, if it requires energy, has a positive delta H, why is it forming? And so this is where entropy is going to come into play. Okay, we talked a little bit about entropy last time. I basically said, don't worry about it too much until we get to chapter 19, which is still kind of true. But you can think about, and this is a bad definition of entropy, but you can think about it in terms of disorder. It's not a good definition. We're going to fix that later on, but I think in terms of a mental exercise for right now, that's an okay way of thinking about it. Okay? So when we mix something, it becomes more disordered, right? And so that entropy has increased, and that allows for the formation of a solution. Okay. Questions on these two figures or anything up to this point? delta H of mixing is still negative, but it hasn't overcome the individual delta H's of solvent and solute. Yes. Is there a set amount that
Like the enthalpy can be,
the enthalpy can be?
yeah, like it could be this much, like positive.
Oh.
At that point, it's like it can't overcome its dual elements.
Okay, so I think you're asking is there a point at which entropy is no longer able to overcome the delta H, the positive value of there? And the answer is yes, but it's not a set number. It's going to be different for every salt or solute solvent mixture. And the reason we know that to be true is the fact that some things don't mix. And so even entropy can't account for allowing that to mix. Which brings us to our next slide. Thank you. Any other questions before I move on? Okay. Okay, so we know that certain solutions, certain liquids don't mix. Great example is oil and water, or even oil and vinegar if you make salad dressing. You know that they don't mix well together. You have to add something like an emulsifier to make that happen. This figure is showing two liquids that do not mix together. You see the line here that's separating those liquids. And then on the other side, you have to sort of trust us, but the test tube has two liquids in it that have formed a solution. This line here is going to be represented in the figure on the right. The defining line between the blue and the yellow. Okay. There's a lot of interactions that need to take place, and they're going to occur at that interface, okay, if mixing is going to occur. Now, what this figure is trying to show you is that there's a lot more pull in terms of molecule A to itself than there is to molecule B or part B. Okay. Is that a question?
Oh, yeah, I was just gonna ask, like, I know when I was in like elementary school, they used to say like density was the reason that it's separated, so I guess how does density flow into the separation of the...
Okay. So how does density and polarity relate in terms of this immiscibility? Okay. So the density will tell you which solution will be on top of the other.
Okay.
But the like dissolves like moniker or polarity, intermolecular attractions are going to tell you whether they will mix.
Okay.
Yeah. So like dissolves like is something you're going to have to think about a lot when you're working on your homework and thinking about will things mix. So what that basically is telling you is that if a solute and solvent have similar intermolecular forces, they have a good chance of mixing. If they don't, they have a bad chance of mixing. The other way of thinking about it is if molecules sort of look alike in terms of their types of bonds, size, shape, they have a good chance of mixing. If they look very different, they don't have a good chance of mixing. Let's see what my next slide is. Okay, so here's our oil and water example. So oil is essentially a triglyceride, and that's what's shown in the box. So we've got a lot of carbon and hydrogen. There is a carbon-oxygen double bond and a carbon-oxygen single bond. So there are some dipole-dipole interactions in this molecule. But the main bulk of it is this carbon-hydrogen chain, hydrocarbon. Water, on the other hand, we know dipole-dipole and hydrogen bonding, and of course dispersion forces and everything. So I guess I answered that question. What types of forces are present in the solvents? So solvents, water, hydrogen bonding, dipole-dipole dispersion. Sorry. There we go. And in terms of the solute, we will have a little bit of dipole-dipole interaction. Are there going to be hydrogen bonds? You're shaking your head no. Very boldly. Do you want to expound on that? Expand on that?
The hydrogen bonds is what keeps the water together. So it's like the lack of the hydrogen bonds in the oil, makes it all
Yeah. So by example, we know that there's probably not hydrogen bonds in oil because if there were, they would have a better chance of mixing with water. That's good. So in order to have the hydrogen bond, you would have to have an oxygen that itself is bounded to hydrogen in the triglyceride, in the fat. But there isn't any. It's carbon-oxygen bonds only. Those cannot form hydrogen bonds. The water cannot hydrogen bond to a carbon-oxygen bond. That's not a hydrogen bond. Is that clear? Does everyone see how that makes sense? Because that's kind of, I know that can be a tricky point. Okay, so our solute, we're going to have dipole-dipole and dispersion. Let me go to the next. So let's look at some examples here with this demo. We're going to try. So, in the flask on the left, we have, or test tube on the left, we have hexane. On the right, we have water. And to the hexane, we're going to add copper chloride. And to the water, we're going to add iodine crystals. Okay. All right, given what you know about intermolecular forces, make a guess as to whether hexane and copper chloride is going to form a solution in hexane, and if iodine is going to form a solution in water. Talk amongst yourselves. You gather up here in a couple seconds. This solution of copper chloride is going to form in hexane. Got a couple? Maybe. All right, what about iodine and water? Okay, a couple. Let's see. All right, so here's our copper chloride. It's a pretty blue color. It doesn't tell me how much, but. All right, so I added the copper chloride. I'm going to mix it with my stir rod. Doesn't look like much is happening. On the iodine side, anyone ever go hiking? Use iodine tablets? for water purification?
I'm not that intense.
Anyone ever use those?
Grab it.
In case of emergency. Alright. What do we see on that one? So I added the iodine. So there's still some iodine crystals at the bottom here in the water, and there's definitely still some copper chloride in the bottom of the hexane. There might be a light brown color in the water, suggesting that maybe some of the iodine has dissolved. So what I'm going to do now is add water to the hexane. Does anyone remember the density, have a guess for the density of hexane versus water? Which one's less dense? I'll say this, it's very similar to gasoline. So it's less dense than water. I'm going to add this. According to the notes, hexane has a density of 0.66. I'm not seeing much color. Oh, maybe a little bit. We got to add more. I think that's the solution.
When in doubt, add more.
That's right. When in doubt, add more. Oh, that's kind of cool. Yeah. Can you guys see a little bit of blue on the bottom? Okay, yeah. Just for good measure. That is cool. See, those are those attractive forces in between the layers there. There we go. Nice. Nice blue color there. Okay, so the iodines, to that side I'm going to add hexane. What do you guys think? Is iodine going to go into hexane? It would be a really dumb demo if it didn't. Okay. Mix this one. Need more, obviously. There we go. What do we see? Yeah, it's turning sort of a red or a pink. The water's kind of brown. Cool. There's still some solid at the bottom of the test tube in the water, but it definitely appears as though the iodine is dissolving in the hexane. All right. Questions on that? So think about the intermolecular forces that are going to be present in these solutes. And maybe you didn't recognize them at first, but now you might have a better sense of what those are. And in terms of their similarity, copper chloride's ionic, okay? Is that similar to water? Not really, but this is definitely very polar, okay? Ionic bonds are polar. Iodine, it doesn't have a polar bond. All right, so this is nonpolar. Okay, no dipole-dipole interactions or hydrogen bonding. Okay, so when you start to look at these things, I want you to be saying to yourself, is it polar or is it nonpolar? If you can break it apart into those two categories, makes things a little bit easier. And you can even do that instead of thinking about the intermolecular forces that are present. Is it polar or is it nonpolar? So let's do this. If it's polar, it might have a dipole, certainly hydrogen bonding. If it's nonpolar, most likely it's dispersion forces that are present. There may be some dipole forces in the oil example here. I'm going to put some small amount of either dipole-dipole or hydrogen bonding. Okay. I think at this point you might be saying to yourself, well, how do we know how much? And I don't have a good answer for you for that because it's not really something that we can quantify in that way. Here. And we'll take a look at our delta H's. For the solvent, again, we're going to have a positive value of delta H. For the solute, positive value of delta H, we got to break apart oil, we got to break apart the water. Our delta H of mixing is going to be a small negative number. And we know it's small simply because we know that the solution, the solution isn't formed. We know that oil and water do not mix, so we're making an educated guess on the size of this delta H of mixing. And that brings us to the fact that delta H for the solution is a big positive number, which would then also suggest that the solution is not going to form. Basically, it's telling us that we need to give it the solution a lot of energy in order to form, and our entropy isn't able. This is something we overcome this. Practice is going to help you with these determining if something is polar or nonpolar. Okay. This is a great example. Okay, so this table is going to show you the solubilities of alcohols in water. This is our first, the second column technically, and then in hexane, which is the last column. We've got, in terms of increasing carbon chain, methanol, ethanol, propanol, butanol, pentanol, and hexanol. If you see the infinity symbol, all right, that basically means miscible. And if something is completely miscible in another substance, it means you could have any ratio of those two substances and they're going to mix. It could be half and half. It'll be fine. It'll mix. It could be 25-75. It could be 75-25. Doesn't matter. They're going to mix. Methanol, ethanol, and propanol are all miscible in water. And there's a decent amount of difference between the structures of propanol and water. And so it's somewhat surprising, right, that these are miscible. But the hydrogen bonding that's present in the alcohols and the dipole-dipole interactions allow that to be the case. As we increase the carbon chain, down the list here, the solubility decreases in water. And that's because our molecules are starting to look less and less like water and starting to look more and more like a nonpolar molecule. So when you see a bunch of carbon and hydrogen in a line, in a chain, or in a cyclic structure, those are going to be nonpolar. So our hexane is a 6-chain carbon. I'm not going to draw all the hydrogens. There's 14 of them. Anywhere I drew a line, there's a carbon bonded. Whoops, can't see that. Okay. And so it might not be too surprising that methanol doesn't dissolve very well in hexane. Hexane. It's a lower solubility than the others, which are completely miscible. And as we go from methanol to ethanol, the structure starts to resemble more like hexane. Okay? So that's a good example of like dissolves like. Yes?
Can you explain what the number means for the solubility? So if it's like 0.11, what does that mean?
So that is given in moles of, it's down at the bottom here, moles of alcohol per 100 grams of solvent. So I mentioned previously that solubility can be given pretty much in any units, whoever wants to write it in. So this book that I got this out of don't think it was your textbook, but the solubility is given in moles of solute per 100 grams of solvent. Okay, good question. What else? All right. Last couple of minutes here. I want you to take a look at these two vitamins, vitamin A and vitamin C, and decide which vitamin is fat soluble in the human body and which is water soluble. And why? In case you're not familiar with these structures, anywhere there's a corner, there's a carbon. There's also some other hydrogens as well. Oops. Yeah, that's right. Is that a question? If you're wondering about the structure of fat, you can go back to the oil structure. It's going to look very similar to that. All right, vitamin A or C, which one is fat soluble? A. It's got a nice long carbon-hydrogen chain. It's going to look a little bit like a triglyceride, like the oil structure we saw. So that means vitamin C is water soluble. Okay. Looks slightly more like water. It's got some OH bonds. Got some nice dipole moments in there. Things like that. A little bit smaller. Okay. Why do I have a pirate? Yeah. Scurvy. If you don't get enough vitamin C, you get scurvy. Okay. A little bit of entertainment. All right. Where are we at? I'm going to touch on this real quick. We have a couple minutes left. I want to look at the temperature and solubility of solids. All right. So this is, we're going to talk mostly about aqueous solutions. And we're looking here at, this figure shows all salts. Sodium nitrate, potassium chloride, sodium chloride. In many situations, you may think that increasing the temperature of a solution may increase the solubility of a substance. We talked about dissolving sugar. We talked about dissolving sodium acetate, and you increase the temperature to help dissolve. That isn't always the case. So if we look, for instance, at cerium sulfate, you'll notice that as the temperature increases, the solubility decreases. Okay? And for those salts where the solubility does increase with increasing temperature, the way in which it increases varies very greatly. So if we look at potassium nitrate, there's a sharp increase in solubility as temperature is increased. But if we compare that to sodium chloride, it's kind of a flatter line. The solubility doesn't increase that much with increasing temperature. Now, there is one thing, the second bullet point here is that, yes, solids can dissolve faster at higher temperatures, but the amount doesn't increase or decrease reliably. Okay? It is actually really hard to predict if a salt is going to increase solubility with increasing temperature. So people do experiments on that. And that's how they get these curves as well. I'll leave you with this. Does the solubility of a gas increase or decrease in aqueous solution with increasing temperature? I want you to write this down, And then I want you to write down why you're making that prediction. So we're just talking about gases.